Episode 6, you built a judge. Today, RL training consumes that signal. Welcome to AI Agents in Depth, Episode 7, Model Post-Training Explained. Build the reward function RL training optimizes, and prove it green with pytest. In Episode 6, you built a judge, a function that scores right answers. Today, reinforcement learning, RL, trains on that score. Here's Chapter 7. Section 7. 1 covers 3 stages: pretraining, SFT supervised fine-tuning, and RL. Every production, LLM went through all 3. Pretraining teaches one thing: predict the next word. Cross-entropy loss, think of it as a surprise score, measures the error. World knowledge goes in. But the model just continues text. It can't answer questions. SFT uses the identical formula. Same surprise score, different data. The diagram makes what changes obvious. Same loss as pretraining, curated demonstrations only. The gradient, the learning signal, only flows through your answer tokens, not the question. Like a teacher marking your answers, not the printed prompt. Misconception. SFT uses a different objective than pretraining. Wrong. Identical cross-entropy. Only the data and masking differ. SFT's ceiling. It can't discover strategies never shown in demonstrations. Imitation can't exceed what was demonstrated. Your turn. Press Control P. Hold Control and tap P. Type agent.py, hit Enter. Judge returns 1 for a correct answer, 0 for wrong. That score is the signal RL training optimizes. Next milestone, we build a reward function that scores a whole trajectory. Supervised fine-tuning copies answers. Reinforcement learning searches for better ones. Here's the loop. The policy, the model's current decision strategy, samples a trajectory. 1 scalar reward scores the whole thing. High reward. That move becomes more likely. That is reinforcement learning. SFT grades every token. RL grades the whole play, then adjusts the strategy. Think of a sports coach watching game tape. High-scoring plays stick. Low-scoring ones fade. That's the gradient update. We build the scoring piece next. Here's why you can't skip SFT, and what the book's experiment proves about RL's ceiling. SFT first, then RL always. Without a warm start, the policy outputs gibberish. Rewards near 0, gradient variance explodes. The book shows RL, then discovers strategies SFT never demonstrated. Now the RL loop itself, the picture behind reinforcement learning. The agent acts, a reward scores the whole trajectory, and the model updates toward higher reward, then repeats, climbing each round. The reward is the whole game. Design it wrong, and the agent games the reward instead of solving the task. Your turn. Reopen the RL loop diagram and trace each node yourself. Trace it. Policy samples, reward scores, gradient updates. Spot where the reward function fits. We build it in the next milestone. Before we write a line, most people think reinforcement learning, RL scores each token as produced. It doesn't. It waits for the whole trajectory. Open agent. Judge is already defined here from EP6. We reuse it, 0 new imports. RL waits until the whole trajectory finishes. Tool calls, observations, final answer, then scores it once. No LLM inside the reward loop. Inconsistent scores are like a noisy referee. The model can't learn which moves actually won. One clear scalar per rollout. A trajectory dict has steps, tool name and result, plus final answer, expected, and min steps. Keep the function pure. No LLM calls inside. Answer score +1 correct, -1 wrong. Tool score 0, 3 per needed call, harder to game. Efficiency -0, 1 per wasted step. Log all 3 to catch reward hacking. That -0, 1 per extra step is carefully tuned. Push it to -0. 5 and the model starts skipping necessary tool calls just to finish fast. The task fails silently. Drop it to -0. 0, 1 and a 2-step solution looks identical to a 10-step one. The training signal disappears. Your turn. Run this in the terminal. Watch each component print. Answer 1, 0 tool 0, 3 efficiency 0, 0 total 1, 3. That's exactly the signal RL training optimizes toward. No model, no GPU, pure Python. Here's the misconception. You need a running model to test a reward function. You don't, it's pure Python. Six episodes of tests right here. Trajectory dicts are plain Python. We build them by hand and call the reward function directly. No API key needed. Correct and efficient scores 1, 3, answer +1, 0, 1 tool +0, 3, no extra steps. Wasteful scores 1, 1, 2 extra steps at -0, 1 each. Wrong answer gets -0. 7, answer -1, 0, tool still +0, 3. 1 assert chains all 3, the exact ranking RL training needs. Best practice. If the reward function can't rank correctly offline, it won't train correctly online. No model, no GPU, no API key. Just Python. Let's run the full suite now. All green, every episode's tests pass. That reward function is the exact signal RL training consumes. Abstract idea is now inspectable Python code. Your turn. Run pytest yourself right now. All green. You just proved a reward signal without any model. Tune the weights here, then hand this function to RL training. You mapped all 3 post-training stages. Pretraining bakes in world knowledge, SFT teaches format by imitation, and RL discovers behaviors no demonstration ever showed. The reward function is the signal RL optimizes. You built it offline and proved its rankings with pytest. No GPU, no API key. Pause here and try this. Handcraft a trajectory where the word count tool is called twice, but the final answer is still correct. Check whether its score falls between the efficient and wasteful cases. Quick check. Does SFT use a different loss formula than pretraining? No, both minimize the identical cross-entropy next token loss. SFT just trains on curated pairs and masks prompt tokens. Second question. Why can RL exceed SFT's capability ceiling? Because RL scores complete trajectories with a scalar reward. It discovers strategies no demonstration ever showed. Next up, Episode 8, Agent Self-Evolution. Follow so you don't miss it.